All right. Hello, everyone. I'm gonna be doing this question right here: physics, electron in a magnetic field. All right. So, an electron that has been accelerated from rest by a potential difference of 250 volts enters a region of magnetic field of strength 0.12 teslas that is directed into the plane of this page. And for question A, the electron's path while in the region of magnetic field is a quarter circle. Show that the speed of the electron after acceleration is 9.4 times 10 to the 6 meters per second. So we're going to do A1 first. And to do this one, first things first is we need to visualize how the electron is being accelerated and what this means. Like, what does that 250 volts mean? So if you imagine, like, let's say there is a two metal plates that has a potential difference of, like, they make a electric field this way. So let's say the electron starts here. Let's use blue. So the electron starts here, and the field lines are like this. So this point, these dashed lines are the points of equipotential, and right here is 250 volts and 0 volts. So the potential difference here is actually the electric potential. And if you remember from like gravitational fields, it's the potential difference is the energy per unit charge. And if you look at the equation here, work, which is the energy, is equal to the charge times the potential difference. And so what this diagram represents, is that if let's say instead of an electron, there was a proton with positive charge. To move the proton from the equipotential point of 0 volts to 250 volts, it's going to take 250 using this equation. The work done to move the proton up to the point of 250 volts is the charge of the proton, which is the elementary charge, so 1.6 times 10 to the negative 19 times by the potential difference, which is 250. In this case, we're working with an electron, so we don't have to put in the work to move the electron to the point of 250, because the electron is oppositely charged to the proton. And so basically nature does the work for us. It's accelerating the electron for us. And so the electron will be accelerated upwards, and we can use the same equation to find the total energy in the electron. So that would be the kinetic energy. It would be the elementary charge. Let me just check if that's correct. So I have the data booklet right here as well. So the elementary charge, 1.6 times 10 to the 19 coulombs, and that's multiplied by the potential difference, which is 250 volts, gives us, let me just do it here, times 10 to the negative 19 times 250. And that gives us 4 times 10 to the minus 17 joules. Okay. And so we have the kinetic energy of the electron. And now we basically need to find the speed of the electron after the acceleration. So we can use the equation of kinetic energy. So let's first equate it to 4 times 10 to the negative 17 joules. And that is equal to 1/2 mass times velocity squared. Let's rearrange this first. So velocity is the square root of 2 times 4 times 10 to the negative 17 over the mass, right? I'll just write that down here right now. and that the mass of an electron is right here, electron rest mass. So I'll just rewrite the equation. It's bad. Right here, and that is 9.11 times 10 to the negative 31 kilograms. All right, now plugging this into our calculator, just give this 2 times 4 times 10 to the negative 17 over 9.11 times gives us this speed, which is equal to 9 point, that looks like 9 million, right? So 9370997.13 meters per second. And judging from the accuracy of the figures, I see the least number of significant figures is 2 significant figures, and so I'm going to round this answer to 2 significant figures. That gives us 99,400,000 meters per second, and we can say that that is 9.4 times 10 to the power of 6 meters per second. And so we were able to show that it is that speed, right? 9.4 times 10 to the 6. Now, how do we show the radius of the path? The radius of this path is 4.5 times 10 to the negative 4. So we can see it says right here it's a quarter circle. So the path, kind of looks like this. And so it's clear that there's a force acting at a right angle called, and in circular motion, that's called the centripetal force. And so what's providing the centripetal force? Well, an electron, the movement of a charge creates a current, movement of charge creates a current, which leads to a creation of a magnetic field. And interacting magnetic fields, the magnetic field generated by the movement of the electron interacting with the uniform field gives rise to a force. Gives rise to a force which helps it travel in this circular path. And so we'll do, I'll do this in green, so A2. And so we're going to equate the FC, the centripetal force, which is, I do remember this, but it is in the forces section right here. So it's going to be, you're going to have to use F equals ma, and then instead of using F equals ma, you substitute v squared over r for a, because that is the rotational equivalent. That's the centripetal acceleration. So it'll be F equals m times v squared over r. And then this is equal to the force given rise, like the force from the motor effect, basically, the left-hand rule, however you learned it. And that force is given by the equation, just go find it. It should be in fields, electric and motor fields. This one right here, motion and electromagnetic fields. It is given by the equation, well, these two equations right here. But since we're dealing with a movement of a charge rather than a current, we're going to use this first equation right here. F equals qvb sine theta. So the centripetal force is provided by the force from the motor effect. And so we're just going to equate this to B QV sine theta. And about the sine theta, the current is moving perpendicular to the uniform field. So I don't know, so let's say we have the 2 bar magnets right here, and the magnets are going out into the page. And so let's say that we're looking from this direction, right? So this is our eye. So this is the direction of the uniform field, and this is the movement of the electron. Now, as you know, in physics, when we talk about current, we're referring to conventional current. And conventional current is the direction is the direction of movement of the positive charges. Although here it's only the movement of electrons, that means it's the opposite direction of the movement of electrons. So the current's going down like this. And so if we look at the angle between, I'll do that in green, the angle between the current and the uniform field, that is 90 degrees. It's a square angle. And sine 90 sine pi over 2 is 1. And so when you and often with our level of physics, we're not going to have to worry about the angles. And so sine pi over 2 is just 1, and so that sign just cancels out, or it just disappears. It just keeps this whole thing whole. And so now we're going to cancel some things out. So you see here v squared, there's a v over this side. We know the v, and we're trying to find the r, the radius. And so we can rearrange this equation to be r equals mass times velocity over the magnetic flux density of the uniform field times by the charge of the electron. And I'm going to do it right on here to save some time. So the radius will be, so the mass of the electron is the electron rest mass, which is 9.11 times 10 to the negative 31. Just check. Yes, it is negative 31. That times by the velocity of the electron, which is given by this answer right here. I'll just copy it over. You'll have to use the store function or the answer function, ANS function, on your calculator. And then the magnetic flux density, that is given by this, 0.12 Teslas. And that is timed by the charge of an electron, which is the elementary charge, 1.6 times 10 to the negative 19. And that gives us, I'm going to, I'll just write out the full, so we'll write out this much times 10 to the negative 4 meters, and we'll round it off. Since we're using the Teslas, again, two significant figures, it's 4.4 times 10 to the negative 4 meters. And that is, I think they might have used different figures. They might have used, I don't know, they may have carried forward, like, let's say they might have used 9.4 times 10 to the 6 rather than the accurate value that we've used. But that is the correct answer. That's the correct method to do so. And yeah, hopefully it wasn't too long. Hopefully I wasn't too long-winded. I did try to get into some of that theory to help you guys understand. All right, hope that was helpful.